Hello, good afternoon student. My name is Hiral Raval. Today's date 8 December 2020. Standard 10th, subject Science. Chapter number 13, Magnetic Effects of Electric Current. Students, this chapter is related to physics. In this chapter, we have performed various activities like activity 13.1. With the help of activity 13.1, we measure the electric current. Then we know about Hans Christian Ørsted. This is the scientist of the 19th century, played a critical role in understanding electromagnetisms. Okay, then we have also studied magnetic field and field lines. In this session, we have studied magnetic field lines with the help of bar magnet and iron filings. This is the diagram of magnetic field lines. Also, we have performed activity 13.3 using bar magnet. Then we have studied magnetic field due to a current carrying conductor. In this activity we use the magnetic compass and we get the deviations in magnetic compass, and we prove that electric current possesses magnetic field. Then we have studied magnetic field due to a current through a straight conductor. In this session, we have studied one of the activity and we derived what happens to the deflections of the compass needle placed at a given point. We shows the pattern of concentrating circles indicating the field lines of a magnetic field around a straight conducting wire. Now in this video we have studied the right hand thumb rule, a convenient way to finding the direction of magnetic field associated with a current carrying conductor is: imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then your fingers will wrap around the conduction in the direction of the field lines of the magnetic field as shown in figure 13.7. This is known as the right hand thumb rule. This is the diagram of right hand thumb rule. In this diagram we show that right hand we have the direction, we shows that the direction of fingers is correspond the magnetic field and the thumb direction is the current directions. Example 13.1. A current through a horizontal power line flows in east to west direction. What is the direction of magnetic field at a point directly below it and at a point directly above it? Solution: the current is in the east-west direction. Applying the right hand thumb rule, we get that the magnetic field at any point below or above the wire. Thirteen point 2.3. Magnetic field due to current through a circular loop. We have so far observed the pattern of the magnetic field lines produced around a current carrying straight wire. Suppose this straight wire is bent in the form of a circular loop and a current is passed through it. How would the magnetic field lines look like? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. This is the direction. We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Similarly, at every point of a current carrying circular loop, the concentric circles representing the magnetic field around it would become larger and larger as we move away from the wire. By the time we reach at the center of the circular loop, the areas of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to the magnetic field, appearing as straight lines at the center of the loop. By applying the right hand rule, it is easy to check that every section on the wire contributes to the magnetic field lines in the same direction within the loop. We know that the magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Therefore, if there is a circular coil having n turns, the field produced is n times as large as that produced by a single turn. This is because the current in each circular turn has the same direction and the field due to each turn then just adds up. Activity 13.6. Take a rectangular cardboard. एक rectangular cardboard हमें लेना है having two holes, जिसके ऊपर दो holes होने चाहिए. Insert it rectangular cardboard having two holes. Insert a circular coil having large number of turns through them normal to the place of the cardboard. Connect the ends of the coil in series with a battery, a key and a rheostat as shown in figure 13.9. Sprinkle iron fillings uniformly on the cardboard. Plug the key. Tap the cardboard gently a few times. Note the pattern of the iron fillings that emerges on the cardboard. Here the activities. Shows the diagram. Magnetic field produced by a current carrying circular coil. Magnetic field due to a current in a solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. The pattern of the magnetic field lines around a current carrying solenoid is shown in figure 13.10. Compare the pattern of the field with the magnetic field around a bar magnet. Do they look similar? क्या वो similar दिखते हैं? Yes, they are similar. In fact, one end of the solenoid behaves as a magnetic north pole, while the other behaves as the south pole. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. When placed inside the coil, the magnet so formed is called an electromagnet. This is the diagram. Figure 13.10. Field lines of the magnetic field through and around a current carrying solenoid. 13.11. A current carrying solenoid coil is used to magnetize steel rod inside it. This is the solenoid. This is the diagram of solenoid. This is the wire, and this is the hollow cylinder. Okay, and this connected with the battery. Here inbuilt questions are there. Then 13.3. Force on a current carrying conductor in a magnetic field. We have learned that an electric current flowing through a conductor produces a magnetic field. The field so produced exerts a force on a magnet placed in the vicinity of the conductor. French scientist André-Marie Ampère, 1775 to 1836, suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. The force due to a magnetic field acting on a current carrying conductor can be demonstrated through the following activity. Here the activity. Activity 13.7. Take a small aluminum rod AB of about 5 cm. Using two connecting wires, suspend it horizontally from a stand as shown in figure 13.12. Place a strong horseshoe magnet. There are various types of magnet like bar magnet, needle magnet, horseshoe magnet, cylindrical magnet. Here we using the horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. For this, put the north pole of the magnet vertically below and south pole vertically above the aluminum rod. Connect the aluminum rod in series with a battery, a key and rheostat. Now pass a current through the aluminum rod from end B to end A. What do you observe? It is observed that the rod is displaced towards the left. रोड जो है वो लेफ्ट साइड डिस्प्लेस हुआ मीन्स कि उसकी मूवमेंट हुई. यू विल नोटिस दैट रोड gets displaced. रिवर्स द डायरेक्शन ऑफ करंट थ्रू द रोड. अभी रिवर्स डायरेक्शन में करो एंड ऑब्जर्व द डायरेक्शन ऑफ द डिस्प्लेसमेंट. तो अब क्या होगा? इट इज़ नाउ टूवर्ड्स द राइट. What does the road get displaced? So the road get displaced in right directions. Okay, तो right and left directions में जो road है वो movement करता है with the direction of electric current. Figure 13.12. A current carrying road AB experiences a force perpendicular to its length and the magnetic field. The displacement of the rod in the above activity suggests that a force is exerted on the current carrying aluminum rod when it is placed in a magnetic field. It also suggests that the direction of force is also reversed when the direction of current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the two poles of the magnet. It is once again observed that the direction of force acting on the current carrying rod gets reversed. It shows that the direction of the force on the conductor depends upon the direction of current and the direction of the magnetic field. Experiments have shows that the displacement of the rod is largest. डिस्प्लेसमेंट जो है वो बहुत ही ज़्यादा होता है, लार्जेस्ट डिप्रेशंस, और द मैग्नीट्यूड ऑफ द फोर्स इज़ द हाईएस्ट, और जो मैग्नीट्यूड होता है वो हाईएस्ट होता है. When the direction of current is at right angles to the direction of the magnetic field, in such a condition, we can use a simple rule to find the direction of the force on the conductor. Here activity 13.7, we considered the direction of the current and that of the magnetic field perpendicular to each other and found that the force is perpendicular to both of them. फोर्स जो है वो perpendicular directions में होता है. The three directions can be illustrated through a simple rule called Fleming's left hand rule. This here the Fleming's left hand rule. According to this rule, अभी जो आगे था वो राइट हैंड रूल था. ओके स्टूडेंट, यहाँ पे लेफ्ट हैंड रूल्स है फ्लेमिंग्स का. फ्लेमिंग्स लेफ्ट हैंड रूल. अकॉर्डिंग टू दिस रूल, stretch the thumb, forefinger and middle finger of your left hand such that they are mutually perpendicular. If the first finger points in the direction of magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion or the force acting on the conductor. Devices that use current carrying conductors and magnetic fields include electric motor, electric generator, loudspeakers, microphones, and measuring instruments. In the next few sections, we shall study about electric motors and generators. ओके, ये जो फ्लेमिंग्स लेफ्ट हैंड रूल्स जो है वो एग्ज़ाम में आता है 2 मार्क्स में। और ये जो यहाँ पे है जो उसका डायग्राम है स्टूडेंट्स, दिस इज़ द डायग्राम। ओके, ये भी हमें ड्रॉ करना है। ओके स्टूडेंट, आज के वीडियो में इतना ही। थैंक यू।